Hey everybody, I am Josh from Anoma, and this is going to be a workshop on VampIR, an LLVM for polynomial circuits. Event is going to be really interactive. I'm just going to do like 5-10 minutes max of intro, and then we're just going to start using VampIR and try to build something with it. I have some ideas of what to do, but it's pretty open for interpretation, so hopefully we have lots of questions and people can bring some ideas as well. But I do have backup in case no one does. Before I do my introduction, if you brought a device, you can go ahead and get a head start on getting VampIR. Probably the best way to get it is to go to github.com/anoma/vampir, dash in it. There's a branch there called ZK Summit, and that branch has a code space that I set up. And if you use the code space version, you'll get semantic highlighting with VampIR because it has an extension built in. If you don't use that, you can also get the binary under releases, or you can build it from source if you wish. If you use those options, you won't get the syntax highlighting. So I recommend doing the code space, but the choice is yours. So if you brought a device and you want to play along, go ahead and you can start getting that. And I'll just go through my first few slides. Just going to be a brief introduction. Oh, this is really important. We have some exclusive VampIR stickers available today, available only to participants in this workshop. They're really cool. They are our cat logo. Let's see if I can show you here. I'm bringing this up now because I don't want to forget to hand these out. So if this thing ends and I have not handed these out, somebody say something.
How do we launch the course of this?
You can go to, there should be a button called Code, green button, and go down and launch it. You do have to be signed in to GitHub, I think, for that to work. Okay.
But I can also just clone and then do it.
Yep. Okay, so I'll just start with introduction to VampIR. The agenda, I basically covered this. For the live coding, I have Blake 2S hash as like an abstract goal. We probably wouldn't finish it, or maybe we would, I don't know. But at least components that would be used there would be useful in many different circuits, so it's a decent thing to start. So why make a language for arithmetic circuits? A while ago, I was asked to see if our MASP, it's a multi-asset shielded pool circuit, would be more efficient using Plonk with lookups than it was with R1CS and Groth16, which is what it was originally written for. The MASP is just a version of sapling with a couple of extra things to allow multiple assets. So I went and I tried to rewrite this in Plonk with lookups, and it was really, really annoying. It was kind of a challenge. I never actually finished that project. And the most frustrating thing about it is that the underlying circuit that you are checking is the exact same if you're using R1CS or Plonk. There's a relation that you are checking. It's the same relation. You just have to express it a little differently depending on the backend that you're using. There's differences in the expression based on proof system, but then also implementations of proof systems can change the way it needs to be expressed. So you have all these different possibilities for how to express one thing which is fundamentally the same thing in a bunch of different places. There really shouldn't, you shouldn't have to rewrite the same circuit in two different ways just to test to see if it's better in one proof system than another. It's just too much time. What is VampIR? This is kind of a aspiration here. We can have VampIRs in IR. The white circles are like front-end languages, ZK languages. You are probably familiar with Socrates and Circom. They've been around for a while. Noir is from Aztec. Heliax has a language called Juvix, which we're going to use as a front end for circuits. And so you can start from any of those front end languages that you see there. And there's a path to VampIR, and then there's a path out of VampIR to any of the backends, which are the black circles on the other side. So any front-end language that wants to hook up to this graph, they can do so by targeting VampIR, or they could target the IR used by Noir. Asir, I think is how they pronounce it, or if you want to use Starks, you can target AirScript. And if we can compile back and forth between these things, then hitting any one of those targets gets you all the options here without having to rewrite anything. That's the big goal. So I'll just talk very briefly about arithmetic circuits and what they are. An arithmetic circuit is a representation of the computation of a polynomial. Here are two circuits. They compute the same polynomial. The polynomials are equal, but the circuits are different because the steps are done in a different order. The circuit on the left is a more efficient way of computing that polynomial, uses fewer operations. So two different circuits, same polynomial. Circuit's a really good word for these objects because they really do function a lot like an actual circuit. If these were printed circuit boards, then you could, I don't know, hook a voltmeter up to one of the nodes and read the value at that node. So each of these nodes has some kind of value that will be applied, the witnesses, and either the circuit runs correctly or it gets fried or something if you don't satisfy it. Another thing is that you can join arithmetic circuits together by basically just wiring them up. Here I have two representations of circuits. This one is div mod, so you take x and y and you get the quotient and remainder out of x divided by y. And then over here we have a range function that tests if something is 4 bits, fits in 4 bits. So by wiring together R and Z, you're forcing those values to be the same value. And so you can compose arithmetic circuits like you would functions. The only thing is you have to designate what the inputs and outputs are, unlike functions which have this feature built in. Circuits basically only have inputs, but you can designate certain ones to be considered inputs and outputs and wire them together and still get some composition. And this is the last slide, I think, on this. Arithmetic circuits are also just systems of polynomial equations. And nothing about them is more difficult than the stuff you did in grade school. This is the system for a range proof of 4 bits here. Maximum degree is 2. And we have 1 polynomial with 5 variables. That's it. It's not that challenging. That's just polynomials underneath. I think, yeah, okay, so now we're going to move on to the live coding portion, with our goal being Blake 2S. We'll see if we get there. We may not. So, a little bit about Blake 2S. This is the more important stuff that we need to do Blake 2S. Actually, what's on the screen will only get us the function that you repeat over and over again for many rounds, this function G. To do the full Blake 2S hash, there's a couple of steps at the beginning and a couple of steps at the end that I didn't put on the screen. But if we get there, then we'll include those as well. If you want to see the full spec for Blake 2S, I have the link up here. Or you can just Google Blake 2S spec or RFC or something, and it'll come up. Okay. So before I switch over to the code, I just want to show what's going on here. This G function, you have a vector of 16 words. Each word is 32 bits. And on each iteration of this function, you select 4 of those 16, and you're only working with those 4. So most of these inputs here are not actually used. A, B, C, and D are the indices of the 4 that you are using in that round. And then there, elsewhere in this, there's a schedule of which ones you use on each round. So V of A and V of B, those are just 2 of the words that we're using. So we'll probably start this just with 4 inputs and not really worry about the whole 16. Then X and Y, I believe, is some extra data that comes in from somewhere else. So we have basically 6 32-bit words, and with those we will add 3 of them together here, do mod 2 to the 32, just to keep the result as 32 bits. Then we have XOR, and we have a rotation. And then all the other steps are just the same. So we need to do mod 2 to the 32. We need to do rotations and XOR and addition. If we can do all of those, then we have the building blocks for this G function. These rotations they're all rotations right. And down here at the bottom of this table, I have the actual amount that you're supposed to rotate So you rotate 16 bits, 12 bits, 8, and then 7. Okay, so we may need to come back to this a couple of times just to see what we're doing, but
Sorry, what
yeah.
are the rounds? It says like rounds in Word, rounds in F, and then we have 10.
Yeah.
And what is F? Is that a field element? No.
Nope. F is another function. F basically has the beginning steps, then 10 rounds in this case of G that you do over and over, and then there's some final bits to F.
Okay.
So F calls G in the middle, and you, yeah. Any other questions over this before we clear it from the screen? We can always come back to it. Okay. All right. These are some slides that I'm probably not going to use very much, showing how VampIR works, but we can just do that in the code space. Oh, and of course, while I was having you guys get code space and everything opened up, I could have been doing that myself. Let's see. Hopefully it doesn't take too long. Oh, perfect. Okay. Okay, so yes, that's exactly what we're doing. Okay. Yeah, well. Okay. Bigger or okay for now? Slightly bigger.
Can you zoom in using your browser instead of the editor?
I don't know. I didn't try it. That works okay. Oh, maybe a little.
Yeah, that's fine. We've got a little bit smaller if you need it, but let's see.
We'll see how it works. Okay. All right, so first we'll just write our first
Maybe the
VampIR statement. We'll write our first VampIR statement here. VampIR has basically two kind of atomic statements. One is a binding and one is a constraint. And even though those words are synonyms, they're treated differently in VampIR. We use the keyword DEF as for binding, and a constraint has an equal sign in it somewhere. Okay, so let's start. We're trying to do mod 2 to the 32. In order to do modular arithmetic, you need a range check. You have to check that the remainder is less than the divisor, right? Otherwise, it's not the correct version. So eventually, we'll be doing a full range check of 32 bits. To get there, we're going to start with a range check for a single bit. So how do you tell that a variable is 1 bit? Does anyone know what constraint you need to say like that x is 1 bit?
Like either 0 or 1?
Yeah.
So just x minus 1.
Yeah. Okay, so okay. That would be a constraint that shows that x is a bit. This constraint is added to, nope, not quite. equals 0. The VampIR compiler will add this constraint to a list of constraints, and the x there will be solicited from the prover when in the proving phase, and a value would be put in there. Then it generates a Planck or Halo 2 or whatever constraint on the backside when you compile the circuit. So that's all that we'll do there. But we don't want to keep writing this over and over again with a new variable name each time. That's annoying, so we would like to use a definition to bind this to something so that we can just reuse it, right? So this is a constraint, but we will change this into a definition. So we do def, let's call it bool x equals, curly braces, need a semicolon at the end outside of the braces. And then inside here, this is basically just a closure that has its own constraints that are generated inside, and then those are appended to the full thing. Inside here, you can put other definitions if you want, constraints, whatever. So what we will do is, the x, we have def bool x, so we are defining a function called bool on an input x. Then we can use x inside, and the compiler will know where to find x because it's the input here. But you can also just conjure up whatever variables you want inside of this as well. And all that's happening there is instead of temporary variables being generated by the compiler, it generates the same temporary variables but gives some of them names if you choose to give them names here. So I could use, I could say y equals t or something inside here. I wouldn't, but I could. The compiler would add y equals t into the constraint system. It'd be pointless here, but you can do it. You don't have to declare every variable.
So,
Yep.
like y and t would be defined globally somewhere else? Or
Yeah, I mean, the variables here are just placeholders that will eventually hold values.
right.
So yeah, they're just added to like a big hash map of variables, and at the end, in the proving phase, the prover will supply values for those, and they'll take on some value. So when you use a variable, even without declaring it, it just gets added to the map. Yeah.
So if you were to write y equals t here and then use bool to generate a lot of constraints, y equals t would just have no effect in the end, right? Because effectively you have two variables that are only constrained by being equal to each other, so you can assign any values to them.
They would almost not have an effect, but the prover would still need to provide values for y and t that are actually equal.
Yeah, sure, but they're not constrained by anything else.
Right.
So yeah.
Exactly. Let's go ahead and put in our Boolean constraint here. So x times x minus 1 equals 0. In the last version of this, I put a semicolon at the end. Here I'm not going to because the last line of every definition does not have a semicolon, and it's the return value. When the return is an equation, it's essentially, I mean, if you know functions, it's returning a unit. It doesn't do anything functionally. There's nothing that happens after that. Instead, that constraint is just like as a side effect added to the constraint system. But you can also put a semicolon here and put x after it. And now, as a side effect, the constraint x times x minus 1 is added to the constraint system. But then if you call this bool x, you actually get a return value that you can use inside of other constraints and definitions.
Sorry. So to be clear, if you had the previous one where you left off the semicolon after the equals 0,
Mhm.
it would just return 0 every time, or what does an equation return?
An equation doesn't really return anything at all. It's like a, yeah, I'm losing the words for it, but yeah, it's just a function with no return. It just has a side effect of adding things to the constraint system. This one has the same side effect, but it also enables bool x or bool whatever, if you call it, to have a value that you can use. Yeah.
A very practical question. Can I use
Mhm.
comments in this VampIR code? Like what's the...
Yeah, 2 slashes.
Okay.
Also, you can do slash asterisk for block comments if you want. Okay, so here's our Boolean constraint. And now I can call bool, let's say bool A. Okay, so this will call this, but with A in place of X. I mean, you guys get this, I'm sure. I will add A times A minus 1 equals 0 to the constraint system. And it has a value of A, which is not being used. That's fine, but it could be used. Let's just go ahead and compile and prove and verify this. Why not? So to compile, the command is, if you're in the code space, you can just use VampIR. It's got the binary loaded into it. If you did this some other way, of course, you'll have to do this a little bit differently, but we'll just use VampIR. Then we choose the backend that we want. We have 2 backends available now. We have Halo2 and Plonk from ZK Garage. If you use Plonk, you have to do a setup. So let's use Halo2 instead, so we can skip that process. We'll do a Plonk one later, but for right now, when we're kind of messing around, we don't want to have to do that every time. Okay, so we'll do VampIR, Halo2, compile. Then dash S for our source. And our source is blake2s.vampire, or if you created your own file, change it appropriately. And then we need to store the output somewhere. So dash O, little o. Let's call this blake2s.halo2. Okay. So this is compilation. What's going on in compilation is the list of constraints is being generated. Definitions are being expanded, and things are being unrolled and added to a constraint system, which is just a list of binary relations. You have like z equals x times y, or z equals x plus y. And everything is broken down into constraints like that. We do have a type checker. You can see, I know it's small down here in the terminal, but it says bool 10 is int to int. So it's a function taking an integer and returning an integer. Then if everything type checks, we synthesize the arithmetic circuit. Synthesis is our word for basically calling the backend and loading the constraints that we generated into the backend. And then it's done. So we just got a binary of a representation of the circuit that was put into Halo 2. Then we can do a proof. So let's do that next. The command is VampIR halo2 prove. To do a proof, you include a circuit, so it's -C. Our circuit was the output of the previous one, so Blake 2s.halo2. And then this will also output a proof in Halo 2, so we need to do -O, Blake 2s dot proof, I guess. So we'll run that command. If you don't include other options, there are some other options for this. If you just run the one that I did, it will solicit the values for the variables from you in the terminal. You can also input the values into like a JSON file, and it will just read them out. But since this is short and easy, terminal's fine. So it's asking us for the value of A. So, okay, A is 1. Okay. Proof is generated here. This is the point where we're really just calling Halo2 with their API. You could also just do this in Halo2 itself at this point. Okay, so we've generated a proof. The proof has not been checked at all at this point. So you could put in whatever you wanted for A. You would still generate a proof, and it would say proof generation success. Doesn't mean that the proof is going to be valid. It just means that you successfully generated a proof. Okay, but next we will verify. So you can probably guess what this is. VampIR halo2 verify. We need the circuit, so -C Blake 2s dot halo2. We need the proof as an input, so -P for proof, Blake 2s dot proof. I want to misspelled everything. Okay. We don't need to output anything. It will just tell us if the proof is valid or not. Okay, so here we go. And proof is valid. So we're good. I put in 1, so the proof is valid. I can easily go back and put in something else, see if we can get an invalid proof. We already did the compilation. We don't need to do that again because the witnesses are not involved in the compilation step. So we'll just do prove again, and this time I'm going to punch some numbers in. Proof generation success, but when I go to verify, I get constraint system failure, which indicates that the proof is invalid. Some of our error messages are a bit esoteric still. But that's proof invalid. Okay. Yeah.
Just to clarify, I'm completely new to zero knowledge, so I'm
Sure.
struggling with some of this. What we have proved here is that 1 is a bit, right?
What we have proved is whatever number the prover put in is either 0 or 1.
Yeah, okay.
But we don't know which one.
Yeah, sure.
Yeah.
It was, okay, yeah, the input was a bit. Yeah.
Yep. Okay. So that's the basics. We're going to build up from this and see how far we can get with Blake 2. We have some really cool new features in VampIR, including mapping, folding, iterating. We have tuples and lists. We can curry functions. We have higher order functions. And that's all enabled by the type checking system. Yeah. Table lookups are not supported directly in VampIR, but it doesn't really matter because what you can do there is put a definition in like this, and a back-end compiler that translates this into, say, Halo 2 or Plonk or whatever, can see that definition, and if it has a lookup available, it can ignore the constraint system stuff in the inside that we told it about, and just do the same thing with the lookup. So yeah, the backend can make that decision. If it has it available, it can swap anything out that it wants. As long as these functions are like specified, then yeah, it can make that change and use lookups. And from the VampIR side of things, it's the same. Well, here, we wrote the backend compiler that translates to Halo 2. And right now, we don't use any of Halo 2's lookups. But we recently found out that at least the way that we're using Halo 2, maybe we can change it, but it's automatically generating a big lookup table for something. We didn't even know that, but it does that apparently automatically, and so we could then use lookups in our compiler to Halo 2 if we want. Yeah.
Maybe a silly question, but like if you would have chips or something that you would already want to use, would that support a thing, or how would you do that?
In the backend compiler, if you can choose to map any of these definitions to a chip, custom gate, whatever, gadget, whatever it's called in the backend.
You can specify that in the backend, like there's somewhere you can go on.
Yep. So yeah, the VampIR language itself is intended to be very minimal so that it doesn't need to know anything at all about front or back end. The less it knows, the better, because it's more easy to target it from multiple front and back ends. Yeah, so it doesn't know about lookups, it doesn't know about custom gates. Back-end compiler that does know about those features in its own back end can make decisions there. Okay. So let's add some more functions here. The goal is to get first goal should be to get a range proof of 32 bits. So here's a range proof of 1 bit. We're going to kind of iterate on this and get a range proof of 32 bits. So one way to do that is we will next make a range circuit for 2 bits. And with that, we can jump up to 4 bits and then 8 bits and just go up like that. So let's try it that way. Okay, so this bool function that we already have, we could also say that this is like range 1 of x. Just to remind ourselves, it's a range of 1 bit. So let's go ahead and try and make a function that does a range of 2 bits. Okay. All right, so the strategy here is we're going to take the input x, we're going to split it into 2 bits. We're going to check that each of those bits is a bit, and also that x actually is the result of packing those 2 bits together. So what we'll do is Inside here, we're going to do a new definition. We'll call this B0 for the low bit. What we need to do here, this is where it gets a little bit funky. In the constraint system, what we would need after this is, well, we don't need anything after this. B0 is just a variable that the prover will supply the value for. However, unlike this expression up here, x times x minus 1, our evaluator will not know how to how to take this input x and compute the correct value for B0. Our evaluator is something that's called automatically in the proving phase. It's not necessary to use our evaluator. Any prover, once they know the circuit, if they know how to generate the witness values, all the values of all the intermediate variables, they can just do that themselves. Really, the necessary part of VampIR is already done by that point. But if you use the VampIR prover, it has an evaluator, and it may not know how to generate some of the values of intermediate variables. So we have a command to give advice to the evaluator on constructing these values. That command is called fresh. Fresh needs parentheses after it. And then inside fresh, you can write an expression that computes the witness value from the input here. So we want this to be the lowest bit of x, so we just want to take mod 2. So we'll do x. We use percent for mod. Okay. So fresh means we are adding a fresh, unconstrained, absolutely free variable into our variable map. And then x mod 2 is saved for later during the proving phase. That way, the prover only needs to give x, and then this is called to help compute B0. Another way to do it is the prover just gives values for x and all the intermediate values in between. That would be a pain, so we have this extra thing. Yes?
Can you run arbitrary code in proving phase, or do you have a restricted library?
We have a restricted library here of operations you can do inside fresh. You can do addition, multiplication. You can do field division, integer division, mod, of course. And we also have another operation which is basically division or 0 if the denominator is 0. It won't fail the division, it will just put a 0 instead for that value, which is actually useful in conditionals, like if you want to do an if statement, you need that.
Do you have a way to access these fresh variable in our circuit, like access for example B0 or?
Yeah, I mean, now we can refer to it as B0.
Right, and you can add further strings.
Yeah, yeah. This is extremely important, and also a reason why we're thinking about removing fresh or rethinking this system. This is a definition. This line has not added any constraints to our system. There's nothing requiring B0 to actually be the first bit of X. We're just saying that when the prover gets to that phase, that's what they should put in order to satisfy the circuit. But no constraints are added at this point. So let's go ahead and add a constraint. We can do that just by saying bool B0. And then, of course, this calls bool, adds a constraint, constraining B0 to be a bit. And now it's good. So yeah, this is a tricky spot where if you forget to add the constraint, then you'll have an under-constrained circuit, which is really bad. So we're thinking about removing fresh and having witness generation handled outside of this document, so that if you're in here, all you see is constraints, and you won't accidentally think that, okay, well, X mod 2 is B0, so it's constrained, because it's not. Okay. Then we're going to repeat this again with B1, the high bit of X. Yeah?
I don't know if you're familiar with circom. Is fresh like the single arrow operator in circom? It sounds like it's...
I haven't used Circom enough to confirm that, but witness generation has to happen for both. There's got to be some way of specifying that, so it sounds like that's doing. But don't quote me too much on that. Okay, so we'll repeat this again. Def B1 equals fresh. This time we need to get the second bit of X, so we'll do X integer division is backslash. So X divided by 2 percent 2. And then bool B1. Okay. So, so we're dividing by 2, so that gets rid of the lower bit, and then we do mod 2 to get the single bit that's of what's left. Okay. All this does is make the prover supply 2 bits called B0 and B1. It doesn't have any connection with X yet. So we need to do that for sure. To do that, we just say X is equal to B0 plus 2 times B1. We will put a semicolon, and our return statement can be X. That way we can use this and get a value out of it. Okay.
Can we iterate under like the scope of the definition, or?
Can you?
Iterate.
Yes. So we will. We'll get to that. You can do iterations. So you can supply an integer value to a function, and it will iterate that many times. So this is kind of like VampIR's version of a loop, but instead of like for loop, you just give a integer. We'll do that. Okay. So here's our range 2. If we want to turn this into something that we can iterate on, we'll need to rewrite this a little bit. Let's see. let's, actually, you know what? For right now, just because my instructions for iterators are on the other screen, let's do a copy and paste. And we'll go up to 4. I'm going to change B0 to low and B1 to high. These bools will change to the range that we just did. And change B0, B1 to low and high. So our goal here is to split X into two 2-bit values and then call the range 2 on those, right? So for fresh here, we'll need the low half is a 2-bit thing, so we'll do mod 4. And then the high is, we'll do X divided by 4 mod 4. And then we'll change this. Should be range, yes, thank you. These should be 8s, not 4s, because they are half of 2 to the 4th. That's where they come from, not the exponents themselves. Okay. All right, and then we change this. Instead of a 2 here, we need 8.
Well, hang on, I have you're dividing the bits of the
Yes. This should definitely be 4.
In the last equation, it should be 8.
All right, well, let's figure this out.
Yeah.
Range 2 is 2 bits, so 0 to 3. If we put in X that is in range 4 bits, so that's 16, right? And yeah, so we just need 2 values from 0 to 3, right, for the low and the high. So
Oh, right, I guess you're right,
yeah, so this is 4.
But you do need to multiply by 4.
Yeah.
It's multiplied by the same thing that you make division.
Yes. And should what? Thank you. Okay. All right. Hopefully that's good because we're just going to copy and paste again and do it again. Yeah.
So what's the difference between division and integer division here? If all of the variables integers here?
Here inside of fresh, I think it wouldn't matter in this case. Yeah. Okay, so this is where it gets a bit funky because in VampIR, all these values are just integers, just big ints. You can use really large integers, but in the back end, everything is converted to a field element. So if you take 2 integers and you do like regular integer division, there's a remainder. But if you're in a field and you do the division on the field elements represented by those integers, then you don't have a remainder, because you can always do division, and you get a different result. So that is why we have division and integer division. Even though everything here is an integer, when it gets to the evaluation phase, we're working with field elements at that point. So it's important to specify integer division versus field division. And the integer division will do the regular integer division before converting into a field, and then the results are the field representations of the quotient and remainder. Okay, so if you want integer division, yeah, you've got to make sure that you're using the integer division symbol, because the other slash will give you something different. Okay. So let's copy and paste this again. And this time we'll go 8. This is the easy part. These should be 4s. The range 2 should be 4s. And let's just think carefully about what these integers should be. We're giving x as an 8-bit value, so we're trying to break it into 2 4-bit values. So we want to do mod 16.
Yeah,
right?
square.
Yeah. And we'll also do the division there. Okay. And 16 at the bottom. Right? Do we agree with this?
I went a little bit ahead of you. I've already tested that code, so yeah, it seems to work.
Great. Perfect. Okay. So we have 16s everywhere. We have range 4s here. Looks good. We'll keep going. We only have 2 more. I don't think we have to talk about these as much. Copy and paste 8 to 16, change the 4s to 8s. And then here, this will be 256, right? Okay. So yeah, I'm on the last one, range 32. Change these to 16. Okay. Now what goes here? Yeah. Well, let's just do 2 to the 16 and save ourselves some mental energy. Okay. Use parentheses. All right. Okay. Yeah, we better stop here and just double check that everything works. So let's go down here and call range 32 on A. And since we've changed the code, we need to recompile, of course. Uh-oh. Oh, yeah, okay. All right. Yeah, this happened recently with exponents. We need to fix, there's an issue on it. What's 2 to the 16? 65536? Okay. We'll use this in the meantime. Okay, now it compiles fine. We see all of our functions there, taking integer to integer. That's good. All right. Then we can just go back up to prove. It's the same command. And it's asking us for A. Let's choose something that should work. You can put things in hex if you want. That should work. So 32 bits is how many in hex? Each byte is 2 characters, so like 8, right? So if I do F, 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 should work. Verify, okay, it's valid. Let's prove again, and then we're going to do 0x. F, 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 F. Proof generation success. Okay, failure. Okay, so yeah, it appears that our range proof is working. You'd want to test this a little bit more, but seems like it's okay. All right, so now we can constrain things to a range. And honestly, this gets us most of the way to what we need for our Blake 2S. Most of it is ranges, weirdly enough. So let's go back to my slide here. Okay, so now we can do mod 2 to the 32. So we can do our first line of this function here. Okay, so that is called G in the RFC, so we'll keep that as well. We're just going to start with 4 inputs. Actually, there's 6, right? There's 4 from the words that are in like this state vector, and then there's 2 other ones. So we'll just do A, B, C, D, X, Y. Yeah, because of our type checker and the way it works, you can just put spaces in between all of these. And the type checker will know that G is the function that we're calling, because we have currying, so this is just automatically handled. And it treats everything essentially the same. Okay, so the first line is we take, let's look at it, A plus B plus X, and then we do mod 2 to 32. So we'll do, oh, and we're putting that back into A. Okay. If I say, A equals here, sorry, if I say def A equals, this will make a new variable, also called A, with a different ID than the A that's up here. If you use def, it's going to create something new. So what we what we will do is, so that means we can just leave this. We're not overwriting A. It's just a new variable, also called A, with an ID that's different. So we're going to save the results of this into a new variable. Okay.
Shadow, presumably you're going to need the original A, the one A that comes from the outside. Shadow this with the entire thing.
Let's see. That's a good question. Really, honestly, we should just use a different variable name.
Speaking as someone who writes compilers for a living,
Yeah.
yes, you should.
Yeah. So let's just do A next. All right, so this will be A plus B plus X, and we want to do the range 32. We need the parentheses there because of the addition that we're doing. Otherwise, if these were like separate inputs, we could just use spaces.
So
Okay.
you're saying all these operations are by default modulo to the 32? Or?
They're only modulo 2 to 32 if we put the range 32 in front.
You mean that we haven't overflowed?
No.
But the Blake the Blake formula had this mod 2 to the 32. Is that Blake specific or is that
Yes.
field element?
Yeah, that's it's part of the Blake spec. They just use 32-bit values to represent the message and everything else. So the integers that we have available here are much larger. So there's nothing naturally constraining them, like when you allocate a variable and you say it's u in 32 or whatever. There's nothing like that. We have to put the constraints in that do that. Okay. Great. So that's the first line. What's the time? Okay.
For overtime. Maybe in the interest of time, you just like the answer.
Yeah, sure. I think this was supposed to be an hour. Am I wrong about that? Or did I just make that assumption? I mean, obviously, you can feel free to leave if you need to go somewhere else. But I think it was originally planned to be an hour.
Yeah, but we are over like 11 minutes.
No,
Are-
it's.
Are we? Oh, yeah, we are. We are.
Yeah.
Wow, okay.
12 minutes ago.
All right. Well, thanks for sticking with me. I apologize.
Maybe
All right.
you're gonna like go fast and just like.
Well, no. I'll just briefly explain the rest of this. There's a bunch of things that we can already do. We can do this step, and this step right now. For XOR, you can return a tuple from a function. So you can take an input and split it up into all its bits, and then actually get the bits back. And then you can do a zip and XOR all the bits together. For rotations, you could also get the bits, unpack it, and then just define equalities for like the new bit stream. But there's actually a better way to do it, which is you can just use mod again. So if you're rotating 16, it's almost the same as a range gate. You split it into the 32-bit thing into two 16-bit things, and then you repack it together in reverse order, and now you've done the rotation. And you can do that for 12, 8, and 7, as long as you have the ability to do mod 2 to the 12, 2 to the 8, and 2 to the 7. We already have 2 of those. We have to just do 2 more. And that pretty much does it for the one round of this G function, it's apply 2. Okay, so
Would you mind completing that and committing it to the repository?
yeah, sure.
Super helpful.
Yeah.
Because,
Yeah, let's go to this. We'll wrap it up here. If you are interested in using VampIR, want to learn more, we have a Discord and of course the GitHub as well. We're chatting on Discord about design changes we want to make. We're writing VampIR. We're trying to include a couple of popular backends, but we really want other people to be able to add their own backends that they want to use and make that easy. So we're thinking about the design of the interface for that. So yeah, if you have questions or suggestions for what you need to see in VampIR, definitely, talk to me or visit the Discord if you want.
not at Discord.
It's a separate Discord from the models. So yeah, I don't know if that's readable here, but that's the invite link. I made it a couple of days ago and it's lasts for 7 days, so if you want to join, we'll do the next couple. I have stickers. So
I think that takes us
that's
by.
it. Thanks everybody.